So the last part has to do with radicals and reducing if the division gives you a fraction exponent. Problem 32 asks me to reduce the cube root of b to the 11th. And although it's not wrong to say that this is b to the 11 over 3 power, that's not desirable. If the division part of simplifying the radical gives you a fraction exponent, that's not the way we're going to want to call it. We won't call that reduced. Even though that's equal, that's not considered reduced. I'm going to reduce this using the prime factor tree strategy. If I want to reduce the cube root of b to the 11th, I'm going to do a prime factor tree for b to the 11th, and that's just simply a sequence of 11 b's being multiplied. So I just wrote down a very carefully selected set of 11 b's. This is a cube root, so anytime I get a 3 of a kind, I get one of those out in front of the radical. Anything that's not part of a 3 of a kind is going to go under my radical and get multiplied back together. So to reduce the cube root of b to the 11th, I'm going to get 1, 2, 3 b's in front of my radicals, because I have 3 groups of 3s from my 11 b's that I wrote down. And under my radical, the single b's that weren't part of a group of 3 go under my radical. For an answer, the 3 b's out front, I'm going to call b cubed. And the 2 b's that I have under, I'm going to multiply and get b squared. So I say the cube root of b to the 11th reduces to b cubed times the cube root of b squared. I can always tell if a radical is reduced because the exponent has to be less than the index. I can't have an exponent equal or bigger than the index for my radical to be reduced. So maybe you can give 31 a go. I'm going to move down to 33, which is your problem. The 4th root of x to the 10th. And 34, which is my problem, the 4th root of w to the 7th. It's a 4th root. I'm going to reduce by prime factor trees. And for letters, a prime factor tree is just writing down as many letters as the exponent tells me. The exponent is 7. So to reduce by prime factor trees, I'm going to write down 7 w's. It's a 4th root. So every time I get a 4 of a kind, I get one out in front of my radical. In this case, I only have one 4 of a kind. And under my radical, I'd get those 3 w's that were left over. I'd multiply those and get w cubed. My answer for 34 is that 4th root of w to the 7th. It's going to reduce to a w in front of the radical, and then under the radical, I get a w cubed for these 3 w's. A radical is never reduced if the exponent is tied or bigger than the index. Next is 35 for you, which is the cube root of x, technically x to the 1st, and 36 for me, which is the cube root of x squared. So this is a cube root. If I do a prime factor tree for x squared, I only get 2 x's, and in a cube root, you need 3 of a kind for it to reduce. This one right here does not reduce. So I probably could just say it doesn't reduce or write the problem back down as my answer. But in order for this to reduce, because it's a cube root, I need to have a 3 of a kind in my prime factoring. 38 is similar. 38 gives me the 5th root of y to the 4th. It's a 5th root, so I need 5 of a kind to reduce my radical. And from y to the 4th, there's not enough y's. You need 5 y's to reduce, so this also is not going to reduce. So maybe I'll just say does not reduce for my answer. And your problem 37 is the fourth root of y squared, and maybe you could say something similar about that. If the exponent is less than the index, it doesn't reduce. The strategy of reducing by dividing, it's not so good, it's not acceptable really if you get a fraction exponent, but in problems 39, the square root of x to the 6, and in problem 40, the cube root of y to the 6, if the exponent, when you divide it by the index, doesn't give you a fraction, that's an acceptable way to reduce. The answer to problem 40 is just going to be y squared. And if I did the prime factor tree approach, in problem 40, this is a cube, so I need to make groups of 3s, and I can show you that if I'm doing it using the prime factor tree approach as opposed to dividing, I should get 2 y's out in front of the radical for the 2 groups of 3. That's the y times y, which is y squared, and you get no y left under the radical because there isn't anything other than a group of 3. So doing the prime factor tree approach, I get 2 y's out in front of my radical, 1 from each group of 3, and I don't have any radical left because there's nothing that's not part of a group of 3. This is why the answer is just a y squared. And this is not a big deal, but you can avoid the prime factor tree approach if the dividing doesn't give you a fraction. If the dividing gives you a fraction, like in problem 34, if the dividing gives you a fraction, then the prime factor tree is the way to reduce. If the dividing the exponent by the index doesn't give you a fraction, that's an alternate way that leads to the same answer, and it's way quicker. So if you look at a problem and you say, oh, in problem 30, 10 divided by 4, to reduce by dividing the exponents, that exponent reduces to a fraction. That's not the way to reduce. But in problem 39, the index is an implied 2. If the dividing the exponent divided by the index doesn't leave the exponent as a fraction, that's the way to reduce. It gives the same answer as the prime factor trees. So if I'm clever, I'll use the tool that's best for my situation. And in your problem 41, as well as my problem 42, the prime factor tree approach will work, but if the exponent divided by the index leaves me with an exponent that's not a fraction, that gives the same answer as the prime factor tree approach, and it's preferred because it's way quicker. The prime factor tree approach is only something that I would do if when you do the dividing, you get a fraction, that the exponent doesn't turn into an integer. 43 is the square root of 50 a b to the 4th. Maybe I'll do that with you. I'm going to reduce each square root separately. I'm going to do the square root of 50, the square root of a, and the square root of b to the 4th. 50 I'm going to do a prime factor tree for, lazily. Well, if I could actually do it. 50 equals shift quotes. 50 is 2 times 5 times 5. So when I go to reduce just the square root of 50, I'm going to get a 2 under from the single 2 in a square root. You need pairs. And a single 5 out front from the pair of 5s. For the square root of a, the prime factoring for a doesn't have a pair, so it's all going to stay under. For the b, I could just divide the exponent, but I'll pretend I didn't notice that. And I'll write down 4 b's forming groups of 2. And this tells me I'm going to get 2 b's in front of my radical and none under, because when I form my groups of 2, there's no b's left over. So in terms of what's going on here, I get a 5 in front of the radical and a 2 under the number radical for the 50. The a is going to remain all under the radical. I'm going to get 2 b's in front of the radical and no b's under the radical. I should probably multiply those two b's together. And for an answer to problem 43, 5b squared times the square root of 2a would be kind of perfect. Okay. Getting to the home stretch is a long section, but a really important section. Problem 48 wants you to do the cube root. For problem 45 wants you to do the cube root of 48 x to the 6 y squared z. And in problem 46, I'm asked to do the cube root, so I need 3 of a kind, of 54 x y to the 6th z to the 7th. Let me do a prime factoring for 54. 54 is 2 times 3 threes. When I go to reduce this, part of my answer is going to have a 3 out in front of the radical and a 2 under the radical, because in a cube root, every time you get 3 of a kind, you get 1 out front. For the x, there's not a 3 of a kind, so it's going to stay under my radical. For the y to the 6th, it would be slick if I just divided its exponent, because the dividing doesn't give me a fraction. It's quicker to simplify by dividing. The alternative way to reduce the y to the 6th would make a group of 6 y's forming groups of 3, and that would tell me I'd get 2 y's out and none under. So the y's is going to be a y squared out. And then for my z's, my z to the 7th, I'm going to write down 7 z's forming groups of 3. The first two groups of 3 tells me I get a z times z, or a z squared in front of my radical, and the straggler z gives me a z under. I don't know how readable that is. My answer for 46 should be 3 y squared and z squared in front of the radical, and then a cube root of 2xz. I'll do 47 with you and skip my 48. Not that it's that much harder. The negative's not such a big deal. So 47, you might want to pause the video and see if you can do this without me. 4 times the square root of 32xy cubed. I'm going to do a prime factoring for 32. Do it by hand because maybe you don't have the technology. 32 is 2 times 16, 2 is prime, 16 is 2 times 8, 2 is prime, 8 is 2 times 4, 2 is prime, 4 is 2 times 2. So 32 is 2 times 2 times 2 times 2 times 2. It's 5 2's being multiplied. It's a square root, so every time I get a 2 of a kind, I get 1 out front. There's a 4 out front to start, and I'm going to bring 2 2's out front from the 2 pairs of 2's, and I'm going to leave a 2 under from the single 2. The single x under my radical is going to stay under because there's not a pair, and I need a pair of them. And for the y cubed, I'm going to get 1 out from the pair of y's and 1 under from the straggler. I'm going to multiply these together. 4 times 2 times 2. 4 times 2 is 8. 8 times 2 is 16. And for an answer to 47, in front of the radical a 16y, under the radical a 2xy. (49) and 50 want me to work with fractions. 49 is the fraction the square root of x over the square root of 16y squared. 50 is the fraction the square root of 106 over b to the 8th. I'm going to reduce each separately. I'm going to do the 106 and the square root of b to the 8th separately. For the b to the 8th, because it's a square root, and because dividing doesn't give me a fraction, it's easier to reduce the denominator by just dividing. So the square root of b to the 8th is going to be b to the 4th. And I'm going to do a prime factor tree for 106. I think that 106 is the one that doesn't reduce. 106, because 106 is 2 times 53, the square root of 106 isn't reducible. It doesn't have any pairs. The numerator is not going to reduce, and it's just going to stay the square root of 106. So my answer for 50 would be the square root of 106 over b to the 4th. 2 problems left. Let's do 51 together, and I'll skip 52. 51 wants me to do the cube root of 81 x y to the 5th over 8. Let me work with each number, the 81 and the 8, the x and the y to the 5th, all kind of separately off to the side to figure out what's going on. I'm going to do a prime factor tree for 81. And that's 3 to the 4th. So it's 3 times 3 times 3 times 3. I'm going to get a 3 out in front of the radical and a 3 under the radical for the 81. The x is going to stay under because I need 3 of a kind in order to get 1 out front, and I don't have that. For the y to the 5th, I have 3 y's and 2 left over. The 3 y's, I'll get 1 out front. The 2 left over will go under and get multiplied. And 8 is 2 times 2 times 2. In the denominator, the cube root of 8 is just going to be 2. And there's going to be no radical in the denominator because the denominator doesn't have anything left over. So I just reduced each piece one at a time. And the answer for problem 51 should be that. So you should attempt to do all the odds in section 4.5. I know I did a couple of them, but I saved most of them for you. It's a hugely important section. The back half of the section, the reducing the radicals, it comes up again and again and again throughout chapter 4 and chapter 5. It's a big deal.